If you could step outside the planet for a moment and look back at Earth the way an astronomer does, the first thing you would notice is not the blue oceans or the white clouds, but the address. Earth is parked in a region we casually call the habitable zone, as if it were a wide neighborhood full of friendly options. In reality, it is closer to a thin ledge on a skyscraper, a narrow band where liquid water can survive on the surface for long stretches of time. Drift a little inward and heat starts to win. Water escapes, chemistry dries out, and the world becomes a furnace. Drift a little outward and cold takes over. Oceans harden into permanent ice, and the surface turns into a locked vault. What is unsettling is not only that Earth lands in the band, but that it sits in a calm middle range, like someone chose the safest seat rather than gambling near the edge. The orbit itself is another quiet advantage. Many worlds swing in stretched ellipses, closer and farther from their stars, lurching through seasonal violence that can reset a planet's surface again and again. Earth's path is close to circular, which means the solar energy arriving each year does not spike and crash like a broken heartbeat. That steadiness is not a luxury, it is time. Early life is a delicate chemistry set, and chemistry hates chaos. Reactions that need consistency cannot thrive if the environment is constantly flipping between extremes. The sun, too, behaves like the right kind of partner. It is not so massive that it burns out quickly, and not so small that the habitable zone shrinks into a hostile ring. It does not lash the surface with constant violent outbursts the way many stars do. It simply shows up, day after day, century after century, delivering stable energy across billions of years. Put these facts together, and the feeling changes. It stops sounding like a story about luck and starts sounding like a story about a system that holds its shape long enough for something fragile to become stubborn, then complex, then self-aware. Earth was not merely in a good place, it stayed good, long enough for intelligence to have the time to arrive and begin asking why the stage looks so carefully arranged. Then there is the water, the feature we treat like a basic background detail because it covers most of the map. But Earth does not just have water in traces, it has an unreasonable amount. Vast basins of liquid that did not freeze solid, did not boil away forever, did not vanish into space in the early chaos. Oceans are not merely scenery, they are regulators. Water absorbs heat slowly and releases it gradually, smoothing temperature swings the way thick walls smooth a fire's warmth. That buffering matters because a planet without it becomes a world of sharp edges, brutal days, brutal nights, climates that lurch rather than breathe. The oceans also make chemistry practical. They dissolve minerals, carry nutrients, and allow molecules to meet repeatedly instead of drifting in isolation. In that sense, the sea is not only a home, but a laboratory with time on its side, where failure does not always mean extinction, where experiments can run for ages. Even the behavior of ice feels strangely helpful. On Earth, ice floats, forming a lid that insulates the water beneath it. During colder stretches, this floating shield prevents entire oceans from freezing from the bottom up. If ice sank, the planet's seas could have become solid blocks, turning early life into a temporary flicker rather than a permanent story. Above the water is air, and Earth's atmosphere behaves like more than a random mix of gases. It is a working system that performs multiple jobs at once. It spreads heat through winds and pressure. It burns up many incoming rocks before they reach the surface, and it filters dangerous ultraviolet light that would otherwise batter living tissue. Its chemistry matters too. Nitrogen provides stability, carbon dioxide helps regulate temperature, and oxygen supports complex organisms. Change these proportions too far in either direction, and the planet becomes harder to live on. Not because life is impossible in principle, but because life becomes a constant emergency. Oxygen is the strangest of the trio because it should not be abundant for long. It is reactive and would vanish into rock if not replenished, and yet Earth maintains it because living organisms make it continuously. That creates a feedback loop that feels almost circular. Life shapes the air supports life, and the whole arrangement holds together like two hands clasped in the dark. Clouds have their own subtle control, reflecting enough sunlight to prevent runaway heating while trapping enough warmth to keep the world from freezing. When you imagine Earth without this atmospheric machinery, it starts to resemble a quieter red planet: thin air, harsh radiation, dry ground, and the sense that biology would struggle to get its footing. Protection is not only about air, it is also about an invisible shield wrapped around the planet, a magnetic field that quietly deflects charged particles streaming from the sun. Without that field, the upper atmosphere would be slowly stripped away, molecule by molecule, and the surface would be exposed to radiation levels that make long-term complexity difficult. The field exists because Earth has a molten iron core that still moves, still churns, still behaves like a dynamo. That internal heat must last for billions of years, and plenty of worlds do not manage it. They cool too fast, their interiors go quiet, and their shields fade. Earth's field has weakened and flipped, but it never abandoned the planet for long, and that continuity matters in a way we rarely credit. Too much radiation breaks DNA faster than life can manage, forcing evolution into a frantic pace that can collapse ecosystems rather than refine them. Earth's shielding keeps mutation within a workable range, allowing slow change instead of constant biological panic. Then there is gravity, a force so ordinary to us that we forget it is another narrow balance. Earth's pull is strong enough to hold oceans and maintain a thick atmosphere, but not so strong that it turns the surface into a heavy, crushing environment that makes complex bodies struggle. A smaller planet loses air over time, water evaporates or freezes, the surface becomes brittle and exposed. A much larger planet could hold an atmosphere so dense that breathing becomes a different challenge entirely, and the mechanics of biology would shift in ways that may limit what organisms can become. Earth's gravity shapes everything, from the way blood circulates to the way skeletons carry weight. It even shapes weather. Rain can fall as nourishment rather than as a constant destructive force. The planet's systems are tuned to this one pull, as if every living design is built around a single calibration. Under our feet, the crust is not dead stone but moving plates, a restless surface that breaks, collides, and reforms. Plate tectonics look violent, yet they act like a planetary life support cycle. Volcanic activity releases carbon dioxide. Rocks and oceans draw it down. The cycle regulates temperature over deep time, preventing Earth from locking into permanent ice or runaway heat. Tectonics also recycle nutrients, bringing essential elements from deep inside the planet and distributing them across continents and seas. Without that long recycling, ecosystems could starve slowly, not dramatically, but inevitably. It is hard to ignore how many of Earth's normal features are in fact ongoing maintenance systems, quietly correcting problems before they become irreversible. The Moon rarely gets treated as part of that maintenance, yet it is one of the most suspicious pieces on the board. Earth's moon is unusually large relative to its planet, and that size gives it leverage over Earth's tilt. With the moon's steady gravitational influence, Earth's axial tilt stays relatively stable over long periods, keeping seasons predictable enough for ecosystems to evolve without constantly being rewritten. Without such stabilization, the tilt could wander chaotically, producing climate whiplash on geological timescales, deserts where forests once grew, frozen belts where warm seas once sepulated, habitats collapsing and reforming too violently for complexity to build. The moon also drives tides, and tides are not merely waves for coastlines. They stir the oceans, mix nutrients, and create dynamic boundary zones where life can adapt to changing conditions, a possible training ground for the transition from sea to land. Even the moon's origin feels like a story balanced on a knife edge, a massive early collision that could have sterilized Earth, yet instead produced a companion at a distance that is neither too close, where tides might shred coastlines, nor too far, where tides would be weak and meaningless. Add to this the underlying chemistry of the planet, the fact that the key ingredients of life are abundant and accessible. Carbon's bonding flexibility allows a vast range of stable yet adaptable molecules. Water supports those molecular interactions as a solvent. Energy is available in multiple forms, from sunlight to geothermal heat to chemical gradients, giving life more than one way to power itself and survive disruptions. But perhaps the greatest advantage is simply time. Earth stayed habitable across billions of years without permanently breaking its major systems. There were impacts, volcanic winters, extinctions, and near misses, yet the oceans did not vanish forever. The atmosphere did not collapse completely. The magnetic field did not die for long, and the climate did not tip past every point of return. Disasters arrived, but they arrived with spacing, leaving room for recovery and reinvention. When you stack these conditions together, the explanation "it was just luck" starts to sound less satisfying, not because design is proven, but because the interlocking nature of the system is hard to dismiss. Water supports climate stability. The atmosphere protects water. The magnetic field protects the atmosphere. Tectonics regulates temperature. The moon stabilizes tilt. Gravity holds the whole arrangement in place. Remove one piece and the structure weakens, sometimes catastrophically. The more we learn, the more Earth stands out as consistently good in every category that matters, not perfect, but resilient. And that leaves an uncomfortable thought hanging in the silence. Maybe worlds like this are not common at all. And if that is true, then life is not only rare, it is precious in the most literal sense.